these are the last set of problems from section 5.2 that I want to go over with you. So these last set of problems, 51, we're trying to find the definite integral now of x squared minus 2 over x plus 1. We're going to ignore the bounds for now and simply look to see what we can do to find the antiderivative. We can't do power rule. We have too many terms in the denominator. U-substitution initially is just not going to work. If we let the u value be denominator, it won't cancel out with the top. If we let the u value be the top, it won't cancel out with the derivative won't cancel out with the bottom. So we look to see if we can rewrite this in a different form, and what we learned from previous problems is that we can use long division. So divisor goes out here, dividend goes inside. First match up the first terms, x and x squared. X times what gives us x squared? X times x. So put x as the first term in the quotient. So take the quotient term, multiply through with every term in the divisor. X times x is x squared. X times 1 is positive x. We draw our line, change our signs. Positive turns to the negative, positive turns to negative. First terms will always cancel out, and they do here. The rest, we look to see if we can combine. These are not like terms, so we put them in order of highest degree first. So negative x comes down first, minus 2. We look to see if we can match up again. X times what gives us negative x, and x times negative 1 will give us what we want. So take the negative 1, multiply through each term in the divisor. Negative 1 times x is negative x. Negative 1 times 1 is a negative 1. Draw our line, change the signs. Negative becomes positive, negative becomes positive. The two x's will cancel out, one negative, one positive, to 0. So we have negative 2 plus 1, which is negative 1. If we look at our divisor, x cannot go into negative 1, so negative 1 is our remainder. To write our remainder, we have it written as the remainder over the divisor because we can't divide any further. So we haven't solved our antiderivative yet. All we've done is we've rewritten the problem in a different form so that we can hopefully apply the rules available to us a little bit easier. So let's look at this problem in a different form. We can use power rule here, and we can use U-substitution. So x becomes x squared over 2. 1 becomes negative x. And here we know that we can go through U-substitution, or we can just see that this derivative will not produce any thing more than the 1. So we can just think of this as 1 over u, which is natural log of u, natural log of x plus 1. So technically I did go through U-substitution, but I'm just going to have everything in terms of x just to make things consistent, allowing us to plug the upper and lower bound in terms of x. So upper bound goes first into each of the x terms. So 4 over 2 minus natural log of 3 minus, now plug in the lower bound. 0 goes in for each of the terms. But if I plug 0 in, natural log of 1 is 0. All these will go to 0. Sometimes we do have to be careful, though. Just because you see one of the bounds being 0, it doesn't necessarily mean that it will just naturally cancel everything out to be 0. So we do have to be careful about this. In this case, they do cancel out, but you do want to make sure and check and plug everything in to make sure. So we're left with 2 minus 2, which is 0. 0 minus negative natural log of 3 is simply negative natural log of 3. All right, 63. F of x is equal to the definite integral from 1 to 3x of 1 over t dt. Find f prime. So if I want to find the derivative of a function that has a definite integral, then I'm going to use second theorem of calculus. So let's set that up. Derivative of the definite integral from 1 to 3x of 1 over t dt. So we learned that with second theorem of calculus that the two operations, the derivative and the antiderivative, will just cancel each other out, leaving this function 1 over t largely unchanged. We just have to make some adjustments with the upper bound. Upper bound needs to be the variable. Bottom bound needs to be the constant. So that is the case in this problem. Plug the upper bound in for the variable of the original function. So that gives us 1 over 3x. multiplied by the upper bound's derivative, so 3x turns into 3. So 3 over 3x is simply reduces to be 1 over x. All right, 69. Definite integral of tangent of x dx from 0 to pi over 4. Now we have a rule directly for tangent of x, no need for U-substitution. Tangent of x becomes negative natural log of absolute value of cosine of x. Plug in we found our antiderivative. No need for U-substitution, so we can keep the bounds the same as before. Plug the upper bound first. Pi over 4 goes in for x. Then plug in the lower bound. 0 goes in for x. We do have to keep track of a lot of negatives here. So cosine of pi over 4 is simply going to be square root of 2 over 2. So that will leave us with negative natural log of square root of 2 over 2. Cosine of 0 is going to be, cosine of 0 is equal to 1 actually. So that's a mistake. It's equal to 1. And we know natural log of 1 is 0. So 2 negatives with a 0 is still a 0. So we're just left with this term here, negative natural log of square root of 2 over 2, which we can use our calculator if we want to simplify this further, which will be 0.3466. Okay, 71. We have a function. We have bounds, x equals 1, x equals 4, and we have the x-axis, which is y equals 0. So it's essentially asking you to find the area of this region. So we can simply write it as the definite integral of our function, x squared plus 4 over x, which looks like this, between the x bounds of 1 and 4. Okay, so now we look to see what rules we can use to find the integral. Notice there's only one term in the denominator. We can split this up into individual fractions. So x squared over x plus 4 over x. This allows us to split up into smaller parts. This first term will just turn into x. Second term, we can simply apply the natural log rule. So 4 over x becomes 4 natural log of absolute value of x. We have the antiderivative. Plug our upper and lower bound. No U-substitution, so we can keep our bounds the same. Plug the upper bound first. 4 goes in for each of the x values. So 4 squared over 2 plus 4 natural log of 4 minus, now plug in the lower bound. 1 goes in for each of the x's, so 1 over 2 plus 4 natural log of 1. Okay. This reduces to be 8 plus 4 natural log of 4. Natural log of 1 goes to 0. Distribute the negative 1 half, a negative 1, so negative 1 times 1 half is negative 1 half. So this is our specific solution, but if we wanted to plug in the calculator, we can write it as a decimal solution, 13.045. Definite integral in this case is we're trying to find the area, so area will be square units. All right, last problem I want to go over is 73. We have our function, we have our bounds 0 and 2, and we have the x-axis. So we're looking to see the area of this region. So we're just trying to find the definite integral of 2 secant of pi x over 6 dx. We have a rule for secant of u, so that will allow us to narrow down our choices for u. We know our u value will simply be what's inside the secant function, which is pi x over 6. So pi x over 6 is our u value. We find the derivative, which is same thing as pi over 6 times x. Coefficient times a variable raised to the first power is simply going to be that coefficient. Cross multiply, dx equals 6 du over pi. Make our substitutions. 2 secant of u times dx gets replaced with 6 over pi du. Coefficients, let's multiply this out and pull to the outside so we can separate separate the parts that still need to be worked on. So 12 over pi, integral of secant of u du. We have a rule for secant of u, which is simply natural log of secant of u plus tangent of u. Notice that we went through U-substitution, and this problem is a definite integral problem. So we do need to go through and change our bounds to be in terms of u. So we look at what's given as our u value, which is pi x over 6. Okay. Our old bound is 0, so plug 0 in for x. So 0 times pi over 6 is simply going to still remain a 0. Our old upper bound was 2. Plug 2 in for x. We get 2 pi over 6, which reduces to be pi over 3. So we have our new upper bound being pi over 3. So now we just want to plug in. Upper bound, the upper bound is pi over 3. Plug in for each of the u values. So we get 12 pi natural log of secant of pi over 3 plus tangent of pi over 3 minus, now plug in the lower bound, 0 goes in for u, minus natural log 12 over pi natural log of secant of 0 plus tangent of 0. Secant of 0 plus tangent of 0 will just come out to be a 1, so natural log of 1 is 0. So all this will just drop out. But we can clean this up. Secant of pi over 3 is 2. Tangent of pi over 3 is root 3. So we do have a specific solution here, 12 over pi times natural log of the absolute value of 2 plus root 3. And if we want to find the decimal value, we can plug in the calculator to get that.